Hi everybody, it's about lab 7, and as you know we totally have like 12 labs, so we're halfway done of all the labs. And today we're talking about moment of inertia. But what does moment of inertia mean? First we need to look at that's related to angle of movement. So actually angle of movement is everywhere when we study human dynamics. For example, when like in rehabilitation we want to know each function of the individual joint. So actually, each joint is an axis of rotation. So like your shank is rotating around the knee, the thigh is rotating around the hip. So each joint is an axis of rotation. Every joint is about angle of movement. And also, if you look at bigger picture, like a golf swing or a baseball batting, it's all about rotational movement. And also in gymnastics. So angular movement is everywhere, and that's pretty important when we want to study human biomechanics. So actually there are several equations that are pretty similar between linear movement and angular movement. For example, when we look at this one, like you're super familiar with, F equals to ma, force equals to mass times acceleration. But actually there is a pretty similar equation here describing angular movement. So this thing is torque, which is a like angular force, right? So torque is correspond with force, and alpha would be angular acceleration, which correspond with linear acceleration. So there should be a mass, like an angular mass, right? So that'll complete this equation, and that angular mass would be the moment of inertia that we want to study today. So when we compare like linear and angular movement, F equals to ma, when you transfer it to angular force, angular acceleration, and angular mass, the equation will be super similar. And also momentum equals to mass times velocity, then angular momentum would equals to moment of inertia times angular velocity. So we want to study the angular mass, which is moment of inertia today. So how do we calculate moment of inertia? We're gonna start with a super simple example. So here is a axis of rotation, and this is a point of mass which is rotating around the axis of rotation, and r is the distance between axis of rotation to the point of mass. So in this case, the moment of inertia would be mr squared, which is mass times the distance squared. So think about it. Do you think the mass will change? Usually not, right? But how about the r, the distance between axis of rotation and the point of mass? Actually, if you move the axis of rotation somewhere else, then the moment of inertia will change. So it's not a little bit different from linear movement. Like in linear movement, the mass is the mass, but in angular movement is related to the axis of rotation. So it's like relative, not absolute mass of angular mass. So if you move your axis of rotation a little bit closer, then the r will change, but the equation will be the same. So in this case, the moment of inertia will be smaller because r decreased, right? Which means it's easier to rotate this thing right now because there's less angular mass. With less mass, it's easier to move it around, right? Okay, so how about a little bit more complicated equation or example? So there are 2 points of mass, m1 and m2. In this case, to calculate the total moment of inertia, actually just sum it up. So that'll be m1 r1 squared plus m2 r2 squared. So that's still not too hard, right? You just get a moment of inertia of these 2 points of mass, and then sum them together. But like this example is still not happening in real world. In real world, it's usually this kind of thing. We want to know the moment of inertia, like how hard it is to swing this baseball bat, right? And there are like infinitive point of masses here around the baseball bat, which is super hard to calculate the moment of inertia. You need like thousands of like single moment of inertia to something up, which is not feasible. Right? So what we want to do is to introduce another equation here to calculate the moment of inertia of like objects in real world. And we're gonna introduce in our next video.